Welcome and thank you for downloading this TU Delft podcast.
Last time Nando did the laminar and turbulent flow again, so no worries, this is called 11 and 12, but I'll just continue. So now we'll start really with chapter 5, because viscous flows is the last part of chapter 4. So now we'll make a start with chapter 5. I got some questions with regard to the separation of a ball, a golf ball or something. Why? So Nando explained a smooth ball and a dimpled ball like a golf ball in a certain flow. Here you have laminar flow and you get, for example, a separation here. What happens then compared to this? You get here turbulent flow. Turbulent flow has more energy inside the boundary layer. You can see that already with a thicker boundary layer, right? Closer to the object, there's more speed, so more energy. And that's due to the fact that you have small scales, sort of small eddies in all directions. Turbulent flow has more energy to fight the adverse pressure gradients. So what will happen is it will separate later, for example here. Now why do you have less drag in this case, less pressure drag? Well, in this case, you get a dead water region here in between. And you can even think of this as a sort of vacuum. So then you have low pressure, right? Well, low pressure here, high pressure here. So it's pushing it in that direction. If you would let this loose, it would travel in that direction, right? So there's a force in that direction. So a drag force. What will happen inside here, of course, there is actually some flow, and it will be entrained here. And here, and quite often you get then vortices, so vortices like this. So they are trained here and go back here and then like this. And that is why, because somebody asked, okay, if I have a vacuum here, of course it would collapse again. But that is not true, because this fills sort of with larger vortices, but there's not actually a streamline from here to here, so you cannot really apply Bernoulli. But you will remain lower pressure behind. So a larger pressure difference over this case than over this case, right? So a larger force, drag force, pressure drag. Okay, let's continue now with chapter 5. So we now move to the airfoils, the wings, and that's this lecture and Monday. And then the aerodynamics is done and you move to flight mechanics. So the beginning of chapter 5 is concerning airfoil theory. So what's happening around an airfoil, the pressure coefficients, how to correct for compressibility, how you obtain lift from the pressure distribution, critical Mach number, and we'll see if we get to the characteristics of finite wings. Now really the core of aerodynamic design, wing design, is an airfoil. So what people start with is airfoil design, and many airfoils have been designed. And what typically is done is then polars are measured. So lift at angles of attack, drag at angles of attack, so lift versus drag. So for the whole range, people, well, they can, of course, simulate it, so compute it, but eventually they will test it in the wind tunnel to evaluate it. And the first thing they do is for infinite wings. They call it infinite wings. What you do then in the wind tunnel, you pretend that the wing is infinitely long, so you have sort of end plates, and ideally as long as possible wing with the same airfoil, and then you can test all the airfoil characteristics. Of course, the realistic wing consists of different sections with different airfoils and is finite. So afterwards, once you have understood sort of the properties of the airfoils, you look at then the sort of sections and you look at the finiteness of the wing. So that's also how we will build now chapter 5 up. And a very famous book is the book by Dunhoff called The Theory of Wing Sections. And that's really sort of the core of an aerodynamic designer. It has wing section characteristics, some things on two-dimensional flows, but also many sort of graphs of airfoils. And that's also at the back of your book. So if you're interested, in Appendix D, I think it is, you have, for some airfoils, the airfoil data. So lift versus angle of attack, drag versus angle of attack, and drag versus lift. Okay. Now, airfoils. There's a very famous series, the NACA airfoil series, and these are developed with specific characteristics. Of course, you can start with a symmetric airfoil. Then, what you typically can change is the thickness. So you have a maximum thickness parameter that is important for your properties of your airfoil. So maximum thickness is typically reported. So the NACA 0012 is non-cambered, 0, and the maximum thickness is 12% of the chord. You express that typically in percentage of the chord. So then you have, but of course we also have cambered airfoils, so not symmetric. This case is symmetric, so the distance to the top and the bottom of the airfoil from the chord line is the same on both sides. But it might also be helpful to camber the airfoil, and that means that you bend the chord line actually, and then sort of you keep still the design of the top and the bottom, and then you can get cambered airfoils like this. And they have then also a certain camber. Yes?
When you say it's 12%, is it the average thickness?
Maximum thickness. It's a maximum thickness. So some important nomenclature of airfoils. Of course, we discussed already leading edge and trailing edge, so front and back. The chord line, that's the shortest distance between the leading edge and the trailing edge. And then there is the mean camber line, and the mean camber line is the line which has the same distance to the top and the bottom. And for a symmetric airfoil, of course, the mean camber line is equal to the chord. But for a cambered airfoil, which is sort of bent, the mean camber line is different from the chord. So as you see here. Then the thickness is like this, and typically what is reported with in airfoil theory is the maximum thickness. Yeah? And in Dutch it's welvingslijn, the camber line. Then two concepts that is important to know. First is the aerodynamic center of an airfoil, and that has to do with moments around the airfoil. Of course, we have forces on the airfoil from the flow, from the pressure and the friction. And as a result, there's also a moment on the airfoil. And there's one point where the moment does not change, or the moment coefficient does not change with angle of attack. So you increase the angle of attack, but the CM, the moment coefficient, remains the same. In general, it's close to the quarter chord point, so 25% of the chord. And this is important to know for stability. So, for example, the center of gravity in relation to the aerodynamic center you should be aware of. So the aerodynamic center is an important aspect for the wing design. Then the center of pressure, and that's the point on the chord where the forces cross, or really are werken, work. So center of pressure, point where the forces are, and aerodynamic center is a point where the moments don't change with the angle of attack. You can look in Anderson, there are some stories about how this is applied and used in airfoil design. At the moment, for the aerodynamics, we will not continue with this, but you will get it back, for example, in the stability and control, flight mechanics. Okay, now airfoils. So these airfoil data I just told you about, most important, or the thing you typically start with, is the CL curve. So that's the CL alpha curve. So here is angle of attack. So increasing angle of attack. So that is the angle the airfoil makes with the incoming flow. So typically the incoming flow is horizontally, and the angle of attack, zero angle of attack. So the airfoil is aligned with the flow. Positive angle of attack, you have a positive angle, negative angle of attack the other way around. And then what is written here is typically CL, so lift coefficient, so dimensionless lift. So it is then made non-dimensional with the dynamic pressure and the area. Now, I drew here so typical CL alpha curves, and what you see, this is for infinite wings. So for infinite wings, you have a very interesting linear lift curve slope here, up to a certain point where you get nonlinear behavior and it nonlinearly collapses. And the direction coefficient, so the steepness of this line is 2 pi, and it's the same for all airfoils. So for infinite wings, the steepness is the same. However, you see here 2 lines for 2 different airfoils, and that is the effect of symmetry versus a cambered airfoil. So this is a symmetric airfoil, and how can you see this is symmetric? Any idea? Yes? Exactly, it passes through 0. So at 0 angle of attack, nothing's really happening. So at 0 angle of attack, the flow passes on top, on bottom. Afterwards, the flow is still horizontal, so there has not been, a force has not been applied to the flow, so no force from the flow on the airfoil, so no lift. Of course, if you have a cambered airfoil, like this, at 0 angle of attack, the mean camber line still has an angle, make sure that you sort of have an angle. So the flow comes horizontally, and due to the camber, and the flow attaches, this is really the attached region, so the flow attaches to the airfoil, follows it, and then here at the trailing edge, it will not go horizontally again, but it will go down. So the flow has been, in a way, pushed by the airfoil from horizontal to downwards, to have a downward component. So it's of course not vertical, but it has a component down. Well, what has done that has to be an external force to the flow, and that's the airfoil. So the airfoil has pushed the flow down, and then you have the law of Newton, action force is equal to the minus reaction force. So that means if you have a stable situation, that the flow has pushed the airfoil up. So that's a lift, a resulting lift. So camber airfoil has a positive lift at 0 angle of attack. And so cambered airfoil need a negative angle of attack to have 0 lift. Now what is happening here? You see increasing lift when you increase the angle of attack. So there's a stronger component of the flow down, right? So the stronger force up to a certain moment. And why is that? What is happening here? That's called the flow separation again. You can imagine if you have 90 degrees of angle of attack, you quite know well that the flow doesn't really follow the object anymore, but you get separation here at both sides and the dead water region behind. You see that if you hold your hand inside a river or so. So of course, that is fully separated from leading edge to trailing edge. So somewhere in between the attached flow, in that case, the flow will start to separate. And that is here. And that phenomenon is called stall. It usually starts somewhere close to the trailing edge with a small bubble because you get separation. Sometimes laminar flow separation, the flow becomes turbulent and reattaches, so you get a small separation zone. But if you increase the angle of attack, the separation will become larger, 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 and at some point you will have leading edge separation. So really separation at leading edge, and that is this picture. So this is a picture of really separation. So this airfoil is stalling, is fully stalled at this angle of attack, and you see the flow is not as though maybe for a tiny, tiny bit following it and then separating. And you get this large vortex in the dead water region. So that's happening there, and that's quite important. So if you see, as you see, the lift drops non-linearly, so quite dangerous. So you should be aware what the stall angle of attack is at certain speeds. And it depends on the speed because the speed is in the CL max. So stall is important. And what is also important is at which lift. So you see there's a difference in angle of attack where the stall happens. So the symmetric airfoil here stalls slightly later, but the cambered airfoil has a higher maximum lift. So a CL max also important, especially when you fly slowly. So what is the maximum lift you can obtain? In this case, that's that one. So the CL max is the top of that graph. Now here are two pictures. So here you have fully attached flow, so no separation, while here it is terribly separated. And in this region, you get sort of from fully attached with a separation bubble to really large separated flow. So that is a nonlinear region. It's very hard to predict computationally. So quite often this is done experimentally. The Navier-Stokes equations, which describe the flow, is a set of partial differential equations, a system of equations. They do have all the scales in them, but we cannot solve them analytically. So what we do, we approximate the flow solution on a certain mesh. And we do that, and the mesh looks like this. So in 2D, for example, you can have structured meshes or non-structured meshes. But what we do is we divide the whole area in sort of small blocks. And we compute the flow in these points. So in these points, we say conservation of mass, momentum, and energy. We apply, instead of continuously everywhere, in these small volumes, and we compute the densities, pressures in these points. Well, if these volumes are large, you miss really the small scales. So the small scales are in the Navier-Stokes equation, but to capture them, to be able to compute them, what did I do? We need very small volumes, but at a certain moment, if you need to do your computation in 3D, we get up to billions of points that we cannot actually solve it, not even on large clusters of computers. Right now, we work with 100 million, 500 million unknowns points on large computer clusters, but still we are not able to capture all these small scales. So what is typically done is we model it. So we model the turbulent scales, because that's the fine scales. We model them, and these models are tuned experimentally on flat plates and everything, and they're typically bad in predicting separated flow. So this is quite a challenge, very important part of aerodynamics. Well, this is for an infinite wing. Of course, true wings are finite. And how finite are they? Well, the definition is then the wing span. So the span is really the distance from one side point of the wing to the other point of the wing for this wing. So the span is b. And then important for the properties of the finite wing, we'll see probably next lecture, Monday, is the aspect ratio. And the aspect ratio tells you how slender the wing is. And the slenderness is measured as span squared. So that's the area you would have if you would have the span squared, so like this, over the actual area. So that's this area. And the more slender the wing is, so the shorter this distance. So then you have a small area related to the span squared. So you have a large aspect ratio wing. So for example, glider wings, have you seen glider wings? They're very thin and long, so they have a high aspect ratio, while sort of commercial aircraft, Boeing 737, have much lower aspect ratios. Well, then important, so what constitutes lift and drag? Well, actually it's the pressures and friction, and very important is the pressure on the airfoil. And an important definition for this is the pressure coefficient. And the pressure coefficient is defined like this, and you really need to know this. So this is a dimensionless pressure, and how do we define it? As a pressure difference. And the difference of P minus P and infinite is the free stream pressure. So you have way before your wing or aircraft, before the flow actually knows there's going to be an aircraft there. So for example, in your wind tunnel, we typically say, okay, we keep the aircraft still and we let the flow over it. So it's the conditions in your wind tunnel upstream of your aircraft. So that's infinite, P infinite, and the dynamic pressure infinite. So the Q infinite, that's half rho V squared. So the CP, you really need to know. So that is P minus P infinite, and the infinite conditions are typically here. So way upstream compared to this airfoil, over Q. And Q is a half rho V squared, right? And well, so any idea what this value is in the stagnation point? So what is CP in the stagnation point? Yes. 0? Oh, okay, let's do it. So with stagnation point, it's up here, eh? So then V is 0. No, it's neither. It's not 0 and it's not a maximum. It's infinite. But the pressure is not 0 in a stagnation point. No, but this is at infinite conditions. This is not at a location. So this is the free stream speed. So this is the V and the rho are the conditions way up here. So 100 meters per second, 1.225 kilograms per meters to the third. So the only thing that's at the location is this guy, right? These are free stream conditions. Anybody? 1? Yeah, close, close. Yes, -1. Perfect. What? Okay, P0. So you agree with me about this, right? Everybody agrees with this? So CP in a stagnation point, let's call it CP, well, Anderson uses a different, so I'll call stagnation. This is a different notation for 0. So CP in a stagnation point is P in a stagnation point, P0 minus P infinite over a half rho V squared. Then let's do the low speed. So let's do Bernoulli. So then we have P plus half rho V squared. Well, let's take this side on the infinite part. Is equal, is constant, right? And it's equal to, say, to the stagnation point on the other side, P0 plus half rho infinite V0 squared. Well, V0 is 0. So I see that P0 is equal to P infinite plus a half rho V squared. So I can take the P infinite to the other side. So I have P0 minus P infinite is equal to a half rho V squared. And then I have that, oh sorry, it's 1. 1 is equal to P0 minus P infinite over a half rho of V squared. So the pressure, so the CP in the stagnation point is actually 1. But why was I confused with the -1? So pressure in the stagnation point is 1. Can it be, is it the maximum that we can have? Can we have pressure below this one? Well, is it? Can we have pressure? So is there any pressure that is higher than P0 in this incompressible setting? No. Okay, so for compressible flows it's a different case, but for incompressible flows, indeed, it is the maximum of your pressure coefficient that occurs, and it's actually 1. Why was I confused with the -1? That's because we normally plot not the CP but the minus CP in our graphs, because the minus CP gives an easier indication. That doesn't matter. You can also plot the CP the other way around. Why do we plot the minus CP? Because now the top airfoil, so CP on top, is here. And then so we have top and bottom CP. And you can easily see, of course, the pressures on the top minus the pressures on the bottom give something like lift. So then the area between this is the lift, and you have the top on top and the bottom on bottom. So that's why we plot here minus CP. But the CP in the stagnation point is 1, and it is the maximum, because there's no, so all CPs larger than that one should be here. It is the maximum CP, but in the minus, of course, not. Yeah? So, and this is then the CP on the upper side. Here is our stagnation point, right? So the leading edge, CP of 1. Then what happens on the upper side and the lower side? Well, on the upper side, we get very low pressures. So low pressures in the minus, the suction area, the suction peak is here, very high, of course, if you put the minus Cp, and then the pressure increases again. On the bottom you have something similar but much less strong. And as you will see later, then the lift is related to this difference. So please be aware, Cp is P minus P infinite over Q infinite. And these are the free stream conditions. And this is the local pressure. So this is the pressure coefficient. Yeah? Question? Oh, yes, sorry. Now, I just showed you the incompressible derivation or the Bernoulli relation that is behind this Cp. Then what happens for compressible flow? So if you have a Cp at a certain point, would be like this, that is very reasonably insensitive to the Mach number for a large range. But if you get close to the Mach number 1, your Cp will change significantly. And Prantl-Glauert have shown that you can work with a correction. It's not valid up to Mach 1 here, but it's valid up to Mach 0.7, and it is a sort of compressibility correction. So this is the incompressible flow Cp, the Cp you would have had if you had incompressible flows. And then if you divide it by 1 minus the free stream Mach number squared and the square root of that, you get the Cp incompressible flows. It's approximation, but it's quite a nice correction which works up to 0.7. Okay. Then an example, 5.11 from Anderson. Pressure on the point of a wing is given of an airplane, 7.58 times 10 to the power 4. And the airplane is flying with a velocity of 70 meters per second at conditions associated with standard altitude of 2,000 meters. And the question is to calculate the pressure coefficient at this point on the wing. Any ideas? How do we start? Hello? No. Sorry? Yes, exactly. We need the standard altitude table for the pressure and densities. Hello? No. Something should pop up here. No, sorry, I'll do it on the blackboard. This is a terrible system. Okay, so we need to look up the table. I did that for you, actually. And then we have that P infinite is 7.95 10 to the power 4. So at standard altitude, appendix A, so P infinite is 7.95 10 to the power 4 newtons per meter squared, and rho is 1.0066 kilograms per meters to the third. Does anybody remember the definition of the pressure coefficient? P minus P infinite by Q infinite. Okay, so P infinite we have, Q infinite, what is Q infinite? Half rho V squared. So that is something we need to compute as well. So Q infinite, half rho infinite, V infinite squared, half 1.0066. The velocity was given 70 squared. So Q infinite is 2466 newtons per meter squared. So now we're there. Pressure coefficient, the pressure in the point was actually given, 7.58. The pressure at free stream conditions is 7.95 times 10 to the power 4 divided by Q infinite, 2466. And then we get a pressure coefficient of minus 1.5. Is this correct? Anything wrong? No, right? We should be worried if it's larger than 1. But if it's, as long as it's smaller than 1, it might be reasonable. So that's always a sanity check you can do in the pressure coefficient. So minus 1.5. Do we need to do a compressible correction, a compressibility, Prandtl-Glauert? No, why not? 70 meters per second. So it's low speed. It's below 100 meters per second. Please be always aware. Some people came to ask me about, I gave you some homework at the end of chapter 4. Also some calculations of pressures. If there is written high speed, you cannot do the Bernoulli, right? So please be aware, we write quite often low speed, high speed, or we give an indication of the speed, like here 70 meters per second. And 70 meters per second, of course, is the speed of the aircraft. On top of the wing, it's probably faster, but let's assume that it's not twice as fast. That's a safe assumption. You should, in an exam, it's wise to add it. So say, I assume incompressible flow because the flight speed is below 100 meters per second. Yes? Okay, let's continue. Any questions? So what we're, of course, ultimately interested in is from this pressure is the terrible thing. Yes? No? Yeah, it's back. From this, to obtain from this pressure, of course, lift. The first step towards lift is the normal force. So what we first compute is normal force, and then we transform the normal force into lift directions. Please, do I have a pen? No, why not? Okay, I'll do it with this. Okay. So what does normal force mean? And what is the direction normal to what? The normal force is normal to the chord. So at 0 angle of attack, the normal force is in the lift direction. But if you have an angle of attack, certain angle of attack, the normal force is normal to the chord, so in that direction, while the lift is normal to the incoming flow, so in that direction. So the larger your angle of attack, the larger the difference between normal force and lift force. Now, let's look at this airfoil up here. Here is our normal direction, normal to the chord, and here is the normal to the surface at that point, because the pressure is always acting normal to the local surface. And I drew then the surface here with the S coordinate, so along the surface, and because we're going to be interested in forces, I look at pressures on areas, right? Pressure is force per area, so if I integrate all the pressures on the area over the area, I get the force. So that's why I take a small slab, and I assume units width, a slab like this with length ds on my airfoil, and I have a certain pressure, and let's assume an infinite wing, sort of that the pressure is as if it is infinite, so it's here the same as here. So I have a certain pressure at this location on my wing, at this small ds, and the pressure is of course acting in this direction. Well, then theta is now the angle between the, let's call it theta, the angle between the normal on the surface and the normal on the chord. So that's up there. Then, not only theta is the angle between the pressure and the normal force, so we have to project the pressure here onto the normal force to get the normal force contribution of this slab, but theta is also the angle between the ds length, that's along the surface, and the dx, that's along the, that would have been the chord, that's the direct line from here to here. Because, why? Because the s is normal to the pressure, right? The chord is normal to the normal force, so I also have a theta between ds and dx. You agree? I'll use that later. No, you don't agree? Anybody doesn't understand? Okay, I'll draw it. So, see if that helps. So suppose I'm here. Then this is my chord line. So my normal force would be a bit like this. Normal direction. While the pressure would act, it's a bit small now. So this is normal to the surface, so this is the pressure. And this is normal to the chord, and that is the normal force line. Yeah? Then I have section ds here, certain section ds. The x is going straight, so with the chord line, like here. Now this is ds, and this is the dx. That is the projection of this ds on the chord. Because I'm going to transform integrations later along my length, my ds, on the chord. So I need to project what I find from this s on the chord. Now what is the angle between ds and dx? Now ds is normal to the pressure, right? So I have here theta. ds is normal to the pressure. dx is normal to the chord. So what this is actually just 90 degrees change of that, right? I just rotate my angles, my pressure and my normal force 90 degrees. And that means that the angle between these is the same as the angle between these. So it's also theta. Yeah? You see that? So it is just rotating. So the pressure, now the pressure is normal to the surface and the normal is normal to the chord. If I rotate it such that this arrow is instead tangential to the surface, then this arrow is in the direction of the chord, and I have also theta in between. Yeah? So that I'm going to use later, so you don't have to understand how we're going to use it, but it might help if you understand how it comes about. Now, what is the normal force actually per meter span on this thing? So suppose we're interested in the overall normal force. That's the contribution of all these to the normal force in that direction, plus the contribution of the normal force of all these in that direction. Now, the normal force of all these is probably close to that direction. However, this one is in the other way. So the net normal force is the projection of these pressures in normal direction minus the pressure on these in normal direction. So on all the slabs. So the normal force is the PL, that's the lower side, and the PU, that's the upper side. And then what is it? The PL is normal to the surface, so we have to transform that to normal to the direction of the normal force. Well, how does this cosine theta ds come in? Sorry? Exactly. So dx is equal to ds cosine theta. So I'll show you again the P and the ds form. So let's go back again. So this is my P, this is my normal force, and this is theta. My normal force contribution. Now, if this is theta, I project it horizontally on this one. So there's here my P is my long side of this. So cosine theta. What is cosine theta equal to? That's P, the normal force contribution. P over the normal force contribution. So the normal force contribution we're looking for. Sorry. So, sorry. So we're putting it here. Cosine theta is A over S. Oh, sorry. It's exactly the other way around. Pardon. So cosine theta is in Dutch de aanliggende zijde over the skewed side. So cosine theta is A over P. Let's call this A. So A, this one, is equal to P cosine theta. Right, we're projecting pressure on the normal direction. Then this is the long side of the 3. Then if this is theta, cosine theta is equal to that one, the shorter, over the long one, so A over P. So then we find that A is equal to P cosine theta. Yeah, you agree? Okay, good. So what we're looking for, the projected pressure on the normal force, is P cosine theta, and we're integrating it still along ds. And then it is the lower side, because that was pushing up, minus the upper side. So P upper is that up here, lower is up there, and we integrate the ds from leading edge to trailing edge. So then we have the pressures all in the normal direction, right? So this is the resulting normal force. Now people like to better work not with this ds, but with the dx along the chord. And then you can transform this one to the chord in a similar way. So in the same way that we can project the pressures, we can project the ds. So we had here the ds, right? So the long side, we project it on the chord line. Then this one is dx. We also had theta in here, the angle theta. So dx is equal to cosine theta ds. So in the same way as the pressure, it's just rotating it, you get that. So what we do is we make this a bit easier, say, okay, cosine theta ds is the same as dx, and the dx is walking from 0 to chord. So this is a nice expression, right? You can imagine normal force, pressure on the lower side integrated from 0 to c dx, minus pressure on the upside from 0 to c dx. Yeah? Then what we typically work with is dimensionless coefficient, so we divide by a dimensionless force, just as we do with lift and drag. The dimensionless force that is typical is the dynamic pressure force. So that is Q, dynamic pressure, so that's newtons per meter squared, times an area, right? So Q times S. Now what is the area here of this thing? Area, any idea? Span times chord. Chord is C, span is 1. So 1 times C, C. So the area is C, so we divide it by half rho V squared C. Now let's put that into here. So we now transform n to dimensionless form. So on this side we get Cn. On this side we also have to divide by Q, half rho V squared, and C. So that's what we do. We put Q in here. So we first divide by Q up there. And we divide by C, we put the C in here. And what we can then do is we transform the integration not from 0 to C, but we can put the C first here, but if we put it in here, we integrate from 0 to 1, dx over C. Yeah? Then the next thing we do is we realize, we have a pressure over a dynamic pressure that's quite close to the pressure coefficient. So it would be nicer, we sort of always talk in dimensionless things, so if we plot the pressure coefficients, might be nice to have pressure coefficients in our normal force computation. How do we get that? Well, we only need this P infinity here. And here we need then minus P infinite. Well, if we do here plus P infinite, we just subtract something and add something to it, so the normal force coefficient will not change. You agree, right? So what I did here is I said, okay, I put minus P infinite here, and then minus minus is plus P infinite here. So I get an even nicer expression of the Cn, so the normal force coefficient, integrating from 0 to 1, x over c. So that's actually integrating, if you would have just x, so from 0 to c. And then the Cp lower minus Cp upper. Yeah? Now what is this? Let's go back to our Cp. So Cp lower minus Cp upper, or Cp low. So we have here minus Cp. So this is minus Cp upper plus Cp lower. So that's actually the area in here. So that is the normal force coefficient, right? The area between the upper and the lower pressure coefficient. Right? Cp lower minus Cp upper, or minus Cp upper plus Cp lower. Actually the area. Okay. Now this is normal forces. Now we need to transform it to lift. So we're almost there. What is the time? Oh, okay. So I'll do the lift and after the break. Okay. So the last lecture. So what is it and how is it used? Reynolds number is rho VL over mu. Rho, density, V, speed, L, a typical length. So this is Reynolds L then at the location L. This is convection phenomena. Flow speed related. Below it's the viscosity coefficient, so this is diffusive viscosity. Now if the viscosity is dominant, so I have something large below, I have a low Reynolds number. That's typically order Reynolds 100 or so. That is if you, for example, would fly through oil. So the viscosity of oil, something like this length. Or a fruit fly, this length through air. Reynolds 100, very viscous. What does it mean? Very thick boundary layers, right? Turbulent boundary layers. Viscous effects are dominant. Viscous effects inside boundary layers. Actually, large vortices. Well, a high Reynolds number, an aircraft flying, so say Boeing, is at millions, order of millions. So very small diffusion phenomena, very strong convection phenomena. What does that mean? Thin boundary layer. In viscid flow, you can assume if you have attached flow outside the boundary layer. So convection is dominant. Yes? Yeah, this L is a typical length. Sorry? Reynolds number at L. So you have Reynolds X, I could say X along a plate, or Reynolds L. Reynolds is a bit flexible, what you fill in here as a length, typical length. So for aircraft wings, you typically look at the chord. So it would be the C. In the length that the flow flows over. How do we use it? Well, we use it, for example, in our wind tunnel tests. Our wind tunnels, aircraft don't fit in. Even the D&W wind tunnel, don't have wind tunnels where a full aircraft fits in, right? So what do you change? You scale the aircraft down. So you change the length. So if we perform a test in our wind tunnel and don't think, we are at the wrong Reynolds number. Well, what does that mean? The flow we see is completely different from what is outside, or might completely be different. Namely, transition point, separation, all these viscous dominated effects will be wrong if you have the wrong Reynolds number. So it's very important to have the similar Reynolds number and the similar Mach number. Then your flow behaves the same. So, for example, if the L changes in our wind tunnel, what we do is we change the V to try to keep the same Reynolds number. And there are even cryogenic wind tunnel in, I think, Stuttgart, somewhere in Germany, where they change the rho and mu. So they work with nitrogen, so different gas, and different temperatures to really try to keep this Reynolds number the same. It's quite an issue in wind tunnel tests. Yeah, so that's why it is important. Then question set 2 was on what was happening here. So I'll do it. Well, question? No? So how the C came in this equation. So I had N is an integral from 0 to C PL dx minus PU dx. What I do then is I divide on this side to make it non-dimensional by QC. So I divide here by QC as well, otherwise I don't have the same equation again. So this is then my normal force coefficient, right? This is my division by Q. This C is constant throughout the integral. So you can do whatever you like. You can take the C outside, then you get the form Cn is 1 over C, integrating from 0 to C PL minus Q infinity dx minus 1 over C, integrating from 0 to C, PU over Q infinity dx, right? You could do this, or you could say, well, I prefer to integrate from 0 to 1. I take the C into my x. So that's what I did here. I said, let's integrate from 0 to 1. The C is constant anyway, so I rescale my x coordinate. So x over C, but then here the integral boundaries change. Then I did something else, because I thought it would be nice to work towards P minus P infinite, and this is the static pressure at freeze. So I need to get the minus P infinite in here. Well, what way can I do that? I can, of course, do minus and plus inside the integral, right? Minus P infinite plus P infinite, nothing will change. So I do the minus P infinite here, and I do the plus P infinite here. Minus, minus. So I do minus P infinite over Q infinite, and here I have minus, minus is plus, so I don't change the integral at all. The final Cn, yeah? And that brings us to this Cp minus Cu integral from 0 to 1. But if you prefer, I would be perfectly happy if you in the exam say Cn is 1 over C from 0 to C integrating dx. It depends on the way pressure is given. I will give you an example later. In Anderson, the pressure is given as a function of x over c. Sometimes it's given as a function of x, but sometimes it's really in points, and you have to integrate numerically. Okay, where were we? Yes, normal force to lift force. So normal force, of course, we were looking for lift force, so actually potential to lift it up. Then the first thing we need to know is the relation between normal forces and lift forces. And there they are. L is n cosine alpha minus A sine alpha. Questions about this, or is it okay? Who would like to get this explained? What's A? Oh, right, yes. That's the tangential flow. So in the normal direction, normal to L. Normal to N. So let's see. I'll draw it for you. What's A? So we have like this. We have V. Well, I make a bit higher angle of attack, sorry, because we don't see otherwise the difference. So horizontal V, this is my chord. So this is the angle of attack, correct? Alpha. Then normal force is normal to the chord. Lift force is normal to the, sorry, probably about here. Lift force is normal to the flow direction, V infinite. Now, what is A? Lift has its counterpart drag, right? That's the force in the same direction as the flow. A is the counterpart of N, so that is in the direction of the chord. Yeah? Now, how does this go about? So we have A between the V and the chord. This one is, the L is orthogonal to the V and orthogonal to the chord. So we have A here too, right? So the N contribution of the normal force to the chord, we project it orthogonally. N is now the long side, so this part is actually, so the long part, the contribution of N in L direction is N cosine alpha, right? Same as we did before. However, this A has also a contribution in the lift direction, right? In this case, negative, so it's pointing here. So we have A up here, where we have the alpha. So we project it again on this side. So this one is then N cosine alpha. While here, where do we have alpha in this case? We have this one orthogonal to this one orthogonal to this one. So this is actually alpha. Yeah? So this one is 90 minus alpha. And you should look up your gonio, but then the contribution of this A, in a way you can see it also here, so alpha, then this is the contribution sinus times A, right? Because it's the short side of this triangle where we have the alpha in here. Yeah? And it's in the negative direction, so that is contributing with minus sinus. So L is n cosine alpha, so projecting the n up here, minus this bit, so the resulting L is a bit smaller, so minus A times sine alpha. And this is then the resulting lift. Yeah? And of course we can do this dimensionless, so we divide each by q infinite c, so we get the CL lift coefficient is Cn normal force coefficient cosine alpha minus C tangential coefficients sinus alpha. Yeah, by dividing of q infinite over c. Now what we do for small angles of attack, we don't like to bother too much about this A, because if you think about small angles of attack, sinus of small angles of attack is close to 0. Sinus 3 degrees is quite small. So up to, I don't know, 5 or 10 degrees, we can assume the sinus alpha is approximately 0, and this cosine alpha is approximately 1. So then, of course, it's not exact anymore, but the first nice approximation is saying, okay, my CL is almost equal to, well, this one drops out, cosine alpha is 1, so it's approximately equal to n. And there we have the different form of the normal force, 1 over c, from 0 to c, this should have been, sorry, dx. C, please. I cannot change it here. The pen doesn't work for some reason. Okay, yeah, clear? So now we have lift approximately for small angles of attack. And I have an example with that. So consider an airfoil with chord length c and running distance x measured along the chord. The leading edge is at x over c 0 and the trailing at x over c is 1. And then the pressure coefficient variations are given here for upper and lower surfaces. So Cp upper for between 0 and 10% of the chord, so 0.1, is given like this, 1 minus 300 x over c squared. On the upper side, the rest, so the first 10% is this one. For the rest, between 10% and 100% of the chord, we have this formula. On the lower side, we have just 1. Cp lower is 1 minus 0.95 x over c. So in this case, it might be easier to use the x over c definition. So integrate from 0 to 1 dx over c, right? But it just depends. Yes? Sorry?
Why do we have the other two approximations when we can just use the third one each time?
Why do we have the other two approximations? Because, sorry?
You can use the third one for every interval because it's from 0 to 1.
The third one. This is on the lower side. This is on the upper side. Yeah? We have two pressures, huh? We have something pushing on the upper side and one pushing on the lower side. So we need actually both. We need the upper side from 0 to 1. So we need both of these for the upper bit. And we need, luckily we have only one for the lower bit. Yeah? Okay, let's do that. Who? Sorry. Yes. Okay. So first, let's try, what is it? Calculate the normal force coefficient. So Cn was integrating from 0 to 1. Let's use that relation. Cp on the lower side minus Cp on the upper side dx over c. So we first need to write down the lower side, CPL, so that's the lowest, so 1 minus, so that's the integral of 0, 1, 1 minus 0.95 x over c dx x over c. Minus, on the upper side, two parts. First from 0 to 0.1. The first one, 1 minus 300 x over c squared dx over c. And then again minus, right? Minus, and the other one still minus. Integral from 0.1 to 1. And that's the other one, minus 2.2777 plus 2.2777 x over c dx over c. Yeah? Questions about this? Now it's straightforward, right? I'll do it quickly. So that we need the primitive values, so 1. So that's x over c between 0 and 1 minus 0.95 x over c. So what's the primitive value of x over c? Yes. Squared over 2. X over c squared, a half x over c squared. Yes? Between 0 and 1. Now, the rest is very easy, similar stuff. So minus, then we have again a 1, so that's x over c. But now between 0.1 and 1, plus, thanks. Between 0 and 0.1, thanks. Plus 300 x over c squared, so the primitive value is x over c to the third dividing by 3, between 0 and 0.1. And the plus is because of the minus, right? Then minus, plus again, so plus 2.2777 x over c between 0.1 and 1 minus, yes, thanks, 2.2777 x over c, so we do the trick again, x over c squared over 2 between 0.1 and 1. Yeah? Trivial, right? Now, quickly evaluate them. So x over c, 1 minus 0, so that's 1 minus, it's again 0 and 0, so we only keep the 1, so minus 0.95 over 2, 475, minus 0.1 minus 0, plus 300 over 3. So that's 100 times 0.1 to the power third is 0.1 plus, now we get 2.277 in 1, so 2.2777 minus the 2.2777 times 0.1, so that's 0.22777 minus, and then we have 1 again, so that's the half of that 1, so that is 1.1388 times 1 plus 1.388 times 0.1 squared, so 0.01388. And then we find 1.4. Yeah? Well, this is just calculator stuff. Or you can do it by hand even, I think. What does this mean? That the normal force coefficient on this section of unit span is 1.4. So it's the normal force is 1.4 times, right? Because this is a normal force coefficient. So Cn is 1.4 is equal to n over Q infinite times C. We have S times 1, right? So the normal force is 1.4 times the dynamic pressure times the chord. Yeah? Okay. Well, if we would have wanted the lift, if it was at small angles of attack, we could also say, okay, then the lift coefficient is the same as well, right? Now this is all with CPs, sort of the incompressible CPs. If we're interested in the higher Mach numbers, we need the same compressibility correction as we did for CPs. So again, the Prandtl-Glauert rule. So the CP, the incompressible pressure coefficient, dividing by 1 over Mach infinity squared. And please note this is at infinity. This is at free stream again. So the compressibly corrected one is this one. Well, of course, 1 is constant. M infinity squared is a constant, so you can take it out. So it's 1 over 1 minus infinity squared. So if we do the same thing as with the pressure coefficient, so we write the CL0 as the incompressible lift coefficient based on the incompressible pressure coefficient, then the compressible corrected one, it is an approximation actually, using the Prandtl-Glauert rule, the compressible corrected CL is this incompressible CL over 1 minus Mach infinity squared. And this is only valid up to Mach infinity about 0.7. Otherwise, if you apply at 1, you get an infinite CL. So it is only an approximation, and it's based actually on this line, the CP line, changing with a Mach number. Oh, shoot, example. 5.17. So we'll do an example with this. So consider NACA 4412 airfoil at an angle of attack of 4 degrees. If the free stream Mach number is 0.7, what is the lift coefficient? Well, it's an easy one, a fast one. So please note, Mach number is 0.7, so we cannot do the incompressible lift coefficient, right? However, incompressible lift coefficients are stored, and for this NACA airfoil, you can look it up in the Appendix D, that the CL is actually 0.83. So that is the CL0. The incompressible lift coefficient is 0.83. Now, what would that mean for the compressible lift coefficient? So we have CL0 is 0.83. How do we get to the CL, the compressible one? Using the Prandtl-Glauert rule, we just divide by 1 minus Mach infinity squared square root. So quite straightforward. But just to show you how you use this, 1 minus Mach number is 0.7 squared. And does it change much? Yes, it does. So you get then a CL not of 0.83, but 1.16. Right? So about almost half higher, a bit less, 30%. At Mach infinity is equal to 0.7. Okay. Now some more definitions. What has actually happened if you increase the Mach number infinity? So there are free stream Mach numbers. So actually the Mach number you're flying at. What is happening? Suppose we have a certain airfoil and we fly at Mach 0.3. Then the flow speeds up here on top. We get a pressure suction area. Flow speeds up and we get a maximum speed, maximum Mach number somewhere on top. And it's slightly higher than the free stream Mach numbers. Let's suppose for this airfoil it's 0.44. So the maximum Mach number, the peak Mach number, is 0.44. Now let's increase our flight speed to 0.5. Then the peak Mach number will increase as well, right? And it's not really linearly, but we get 0.71. Let's further increase. For this airfoil, Mach is 0.6. Then our peak Mach number for a certain flight Mach number, free stream Mach number, we will have the first time that we get sonic flow somewhere. That actually the speed in a point is the same as the speed of sound in that point. Mach 1. The peak Mach number of 1. And we call this the critical Mach number. And it depends on your airfoil actually for which Mach number it will occur, right? If it's very thick, it will speed up more here, and you will get a different critical Mach number. So the critical Mach number for the airfoil is the Mach number at which you fly, such that the peak Mach number, the highest Mach number in the flow, is equal to 1. Yeah? Well, we go further later. So how is this then related? Let's see sort of our Mach number here. We have a certain critical Mach number such that we have Mach 1. Now this is actually related to our pressure coefficient. If we have a very thick airfoil, we will have a Mach number which is way below 1, such that our peak Mach number on some point in the airfoil, probably there, will be 1. So this is then the critical Mach number. And if we look at the CP plot, you will see that the CP will be really sort of in the minus sign, so we have strong pressure changes, this means. So we have the minimum pressure is in this case minus 1.5, so the minimum pressure is this plot again, but it reaches here Mach 1 very closely. And then this is called also the critical pressure coefficient. And that is the critical pressure coefficient here is also a function of the airfoil and a function of the Mach number. If we have a thinner airfoil, we have to fly faster, right? It's disturbing the flow less. We have to fly faster to reach a Mach number of 1 somewhere in the flow. And the resulting pressure coefficient looks like this. And even thinner like this. So there's a relation between thickness, critical Mach number, and critical pressure coefficient. Yes? The critical pressure coefficient is the pressure coefficient at which you will have Mach 1. So it's sort of the counterpart of the critical Mach number in a way. The only, it is, what you should take away with you is that there is a relation to pressure coefficients are related to pressure changes, right? So a pressure coefficient in a certain point is saying how the pressure is lower than the free stream pressure. If your airfoil is thicker, you have a further, earlier, at lower speeds that Mach reaches 1 around your airfoil, right? So you have a lower critical Mach number. What will happen to the pressure coefficient? What is the pressure coefficient at that point? So the minimum pressure coefficient you will reach, because the minimum pressure coefficient is in that maximum point where you have Mach 1. The critical pressure coefficient there is really lower because the P minus P infinite is larger if you have a higher difference. So the only thing you should sort of be aware of, the critical pressure coefficient is then the pressure coefficient at which, the point at which you have this Mach 1. And that is a function of your thickness. That is really the main point to take away of. Now, what we're working our way towards is a definition of the critical pressure coefficient. So let's start at the end. So the critical pressure coefficient is the pressure coefficient for this point at which you reach for the first time Mach 1. Would be nice if we have an expression of this as a function of the Mach number. And here it is. So here's our critical pressure coefficients minus Cp actually as a function of the Mach number. So for very high Mach numbers, if we fly at Mach 1, we have Mach 1 at free stream already, right? If we fly at Mach 1, so m infinity is 1, we have at free stream, so at p infinity, we have Mach 1. So then Cp was p minus p infinity, so we have p infinity minus p infinity, 0. So then the critical pressure coefficient is 0. And the lower the Mach number is, the higher the minus Cp, so the lower your critical pressure coefficient is. And how can you derive this? So you can derive the function for the critical pressure coefficient. It looks a bit complex, but it is not that complex actually. I'll take you through it. Do you have to know this? No. What you have to know, so you don't have to derive this yourself. I will write on the blackboard, I forgot, sorry, which derivations you need to know for the exam. That's actually Bernoulli energy isentropic flow number 2. Yes. Please be quiet. I cannot hear the question. Yes. Good point. This Mach number is the flight speed. So it's a function of m infinity. I should have infinite. Because here you see what I end up with. It's just a function of infinite Mach number. Yeah?
This is the actual velocity the body is going at, and not just...
Yes, so the Mach number is the actual velocity the body is at, and it tells you the critical pressure coefficient in the point where you have Mach 1. So where you will reach the Mach 1 the first.
Okay, so when the flow reaches Mach 1 along the body, or when the body itself is going at Mach 1?
No, when some point in the flow reaches Mach 1, and then the critical Mach pressure coefficient is the pressure coefficient actually in that point in the flow, and it is then the minimum pressure coefficient. No one will, that's where it is fastest, your flow, so no point will have a lower pressure coefficient than that one.
Than the one going at
Yes, yes. That's this Cp. So how do you derive this? Well, of course we need the definition of Cp. P minus P infinity over Q infinity. And we like Mach numbers in here. So the first thing we realize is that Mach numbers need speeds of sound, right? And speeds of sound, I derived a while ago, are a function of, it's gamma rho t, square root, right? So speed of sound squared is gamma RT. Yeah? A squared is gamma RT is same as gamma P over rho, right? Because with the equation of state, P is rho RT. So if we had ratios of P over rho, for example at infinity, we can get A in there. So what I'm going to do is rewrite this such that I have nice ratios of P over rho, P infinite over Q infinite. Then I have a minus 1 here and a P over P infinite here. So then I have here P infinite, so P over P infinite times P infinite. So this one drops out. So P over Q minus P infinite over Q. Then I realize that Q is half rho V squared. And I can get the gamma P in here. So a half rho dividing by gamma P times gamma P V squared. And then this portion is actually gamma P over rho 1 over. You see it? So I have in that bit, I have rho infinite over gamma P infinite. Well, A squared is gamma P over rho. So rho divided by gamma over P is 1 over A infinite squared, right? So in here, I divide by gamma P on the upper side and the lower side. And then I realize that I have here rho over gamma P. And that's the same as 1 over gamma p over rho, and this is a squared. So I get my mag squared in here, v squared over a squared times gamma p. So Q infinite is a half v squared over a squared gamma p, so a half mag squared p at free stream. Yeah? So I rewrote this Q infinite, I have this Cp. What I then need is the isentropic flow relations, and I'm going to use two isentropic flow relations relating pressures to Mach numbers. I want to get sort of a nice Cp critical as a function of Mach number. Well, I have these, but here I have the stagnation pressure. I don't have the stagnation pressure anywhere here. So to get that out of the way, I use two isentropic flow relations, one at P, so at this point, at A point, and one at P infinite. So then for at P, I have this isentropic flow relation, P0, stagnation pressure over P in a certain point is 1 plus gamma minus 1 over 2 m in this certain point, where this P is to the power this. And if I have P infinite here, I have M infinite here, right? Now what I do, I divide these to get rid of the P0. So that's the next step. So I divide this one by that one, so I get P0 over P infinite. No? Yeah, I wish I had the pen. So P0 over P infinite. P0 over P infinite dividing by P. 0 over P. Yeah? Dividing by this one is multiplying by the inverse, so this is the same as P0 over P infinite times P over P0. Yeah? So I get the ratio P over EP infinite. So taking the P0 over EP infinite, dividing the P0 by P. So doing that, I divide this one with the mag infinite squared over that one with the mag. So I get this one with the mag infinite squared dividing the same one with the mag. So now I have a pressure ratio. What I now do, we were looking at critical pressure coefficient, right? So I need the critical pressure coefficient again. So I need to substitute this in the pressure coefficient relation. And I derived earlier that that the pressure coefficient can also be written like this, right? P infinite over Q infinite, P over P infinite minus 1. Now this one I have up here. So that is up this one minus 1. Then the P over Q infinite, on the earlier page, I showed that the P over Q infinite you can find from here. P infinite over Q infinite is 1 over a half mag squared. So there it is. There's this one. So then we get Cp, so we can take here out the divide by the pressure. We get the relation for a pressure coefficient. This is not critical yet, this is a pressure coefficient. Pressure coefficient relating the pressure in a certain point to a pressure in the free stream, right? Cp. And what you see is that it's a function of the Mach numbers. Mach number at infinity and the Mach number at the pressure point, P. Now how do I get the critical pressure coefficients? Mach 1. Which Mach? This one, eh? Indeed. So what is the critical pressure coefficient? That is the pressure coefficient, so the critical pressure coefficient. Cp critical is P minus P infinite over Q infinite. And this is then the P. So this is at the point where mag is 1. So fill in M is 1, and then we find this relation. And then nice, very nice, you see that the pressure, critical pressure coefficient, no, not nice, is the minimum of what that occurs, is a function of the mag number only. The free stream mag number. And if you plot it, it's sort of a parabola like this. Yeah? So if you fly fast, it's not so surprising this, right? If you fly fast, you need only a small pressure difference related to the free stream pressure to get to Mach 1. If you don't fly fast, so you fly slowly, you have Mach 0.3 or 0.4, you need a large pressure difference to speed the flow up from 0.4 to 1, because this pressure difference is speeding the flow up, yeah? Then a few more minutes, eh? 1, okay. No, just enough to introduce you to the drag divergence, and then I let you go. Drag divergence. I just introduced critical Mach number. Critical Mach number is the Mach number at which we fly for a certain airfoil such that we get a point, a sonic point somewhere. Not a supersonic area, not a shock shed yet, just a point where the speed is equal to the speed of sound. If I increase my Mach number, if I go faster, so this is my, if I'm below the critical Mach number, I have subsonic flow everywhere. If I'm at the critical Mach number, I have it in 1 point. If I'm slightly above the critical Mach number, I have a very, very small blob of supersonic flow. So the flow is speeded up here on top of the airfoil beyond the speed of sound, and then slowed down again. Very weak shock, very small area, not a major effect yet. But if I increase the Mach number further and further, I get a larger portion of supersonic flow, right? At some point, very large portion, and I get, so the flow is speeding up beyond the speed of sound, so supersonic flow. At some point, I hear again, I have subsonic flow behind my airfoil, and the flow is slowing down with a shock wave, so a jump here to subsonic flow. And this shock, what it actually is a very dissipative, on a very small scale, lots of dissipation. So what does this shock do actually? What does it do to the drag of your airfoil? Go down or up if you have a shock? Up, yes. And it goes up a lot, not only because you have dissipation here, but due to this dissipation, quite often you get a separation as well. So you get an increased friction drag and increased pressure drag due to the separation region. So if you're flying above the drag divergence Mach number, you get this situation, and you have then a diverging drag, so it's fastly increasing, so diverging drag. And this is what you would like to prevent, right? Sometimes it's not possible, but sometimes people design sort of critical airfoils, supercritical airfoils, such that that we try to avoid this situation and try to stay in this situation. Not always possible, but very important for an airfoil is the drag divergence Mach number, right? So please know the definition of drag divergence Mach number. And then I have 2 homework questions for you about this chapter 5, 5.8, 5.14. And then I see you on Monday for the last bit on finite wings. Thank you.
Please visit our OpenCourseware website for more information. See you at our next podcast.